Alright, so this is the first time I actually solve an equation of the day on video, and that's because I just think there's a lot you can learn here. I think that solving it is pretty easy, but solving it in a smart and fast and productive way is not that trivial. And I also, for me, the point of having these equations of the day is not so you can just it's not only so you can just have fun solving these, but also for people to learn math and improve. And I haven't yet seen a solution that also explains the way of solving for those who don't already know how to solve these types of equations and problems. So that's what I'm gonna do today. I'm gonna explain it from scratch. First of all, before we get into the problem itself, I want to explain what the choose function is. Now, if you already know that, if you are already familiar with the choose function, I'm not gonna tell you when to skip in the video because I'm not gonna edit it. I have to do something after this, but I am gonna take I don't know, a red pen, and I'm gonna do this. Alright, so when you see this, you can skip ahead until you see this red sploosh, and when you see it, you know I already finished talking about the choose function. But before you do it, before you skip ahead, I'm not only gonna talk about what the choose function is, but I'm also gonna prove the choose function, like its expansion. If you're interested in that, you can also stay and watch. So what is the choose function? Basically, as you may already know, there's the factorial function, which takes, I don't know, let's say I have x cards, okay, numbered from 1 to x. X factorial basically gives me the number of different way I can arrange these x cards. Okay, so it can be 1, 2, 3, 4, 5, 6, 7, 8, all the way to x. It can be 1, 3, 2, x minus 1, 9, x, 10, 8, 6. It can be any different way. X factorial measures the number of ways it can be arranged in. Now, how do I calculate it? Very easy. For the first spot, let's take this 12 circles, 12 spots already prepared for the question as an example. First of all, I have, and of course I have 12 cards numbered 1 through 12, right? So for the first one, I can put either the card numbered 1, I can put the card numbered 2, I can put the card numbered 3, all the way up to 12. So I have 12 options for this one. For the next one, I have only 11 options, right? Because let's say I already put here a 3. Here I have all the numbers from 1 to 12, but I cannot put here a 3. So I have only 11 options. Now let's say I put here a 5. Now I have two cards already taken. I'm left with 10 cards to put here. So this has 10 options, and so on. And this has 9 and 8, blah, blah, blah. Now, what do I know from this? Well, for each of the 12 cards that I put here, I have 11 cards to put here, right? Because I can put here 1, and then I have 2 to 12. I can put here a 2, and then I have 1, and then 3 to 12. I can put here a 3, and then I have 1, 2, and then 4 to 12. So for each of the 12 options, I have 11 different options. How do we calculate it? By multiplying. So I have, for the first two spots, 12 times 11 options, right? If I keep going, for each 2 cards that I put here, I have 10 options, which will give me 12 times 11 times 12 total different ways to put 3 cards in these, and so on. So x factorial basically equals to x times x minus 1 times x minus 2, and so on until I have only one option left here. I got a bit sidetracked, but I just remember that not everybody necessarily knows what a factorial is, so now you know. What is the choose function? The The choose function is another different function like the factorial that helps us with arrangements. It can be written in two ways, actually three I guess. N choose R can be written as this N and then capital C and R. This R kind of looks like an N. It can be written as N C R like this, and it can be written as N and R in parentheses. This is the one I'm gonna use just because I think it's the most visually pleasing. This one isn't really used. This one is mainly for calculators. Like this is what you see on a calculator when you want to use the choose function. So what is the choose function? Basically, let's say I have n spots and I want to choose randomly r spots from them, but I do not care about the order. For example, I have n lamps, okay, and I'm asking you how many ways can I lit up r lamps from them. Now I do not care if for example I light up this lamp and this lamp. I do not care which lamp is lit first, right? In the cards example we have 3 here and 5 here, but we can also have, for example, we can also have 5 here and 3 here. These are different. In this example I do not care because it's either lit or not lit. So this is lit, this is lit, and I cannot swap between them. It will be the same. So obviously I will have less options. This is n choose r. Now the equation for n choose r is as follows, and now we're going to prove it. The first thing I want to say is that you can take it as an exercise. There's an easy way to prove it and a hard way to prove it. I personally, when I was in 10th grade, I wanted to prove it really hard and I spent like months on it. It took me a long time and I did it the hard way. I did it through looking at different examples from a small n, like n equals 1, n equals 2, noticing a pattern. Then I remember connecting it to Pascal's triangle, and that was just a big mess. It took me a long time. Eventually I did get to the correct solution, but there's a way easier method. And in order to get to this method, you have to actually understand the difference between the choose function and the factorial and how they work together in probability problems. So I'm going to explain it now. The easier way to prove it is as follows. Let's say I have n cards numbered 1 through n, right? So I have 1, 2, 3, 4, all the way up to n. And I'm asking you, what is the probability that I'm taking r cards from this and they are consecutive numbers? Okay, I'm choosing r cards. This is why it's called the choose function, by the way. I'm choosing r cards. What is the probability that they are consecutive? Okay, no, sorry, I'm gonna make a correction. What is the probability that these are the first r numbers, which means I pick r cards and I get 1, 2, 3, 4, 5, 6 all the way up to r. So we have two ways to solve this, actually. The first one is just saying, okay, how many total possibilities do we have? We have, let's say, okay, let's say I'm arranging these n cards, I'm shuffling them, and then I just pick from the top the first r cards, right? This is the same thing, like I've said before. This is just choosing r random cards, but I'm doing it in a way which allows me to calculate it easier. So I'm shuffling the deck. Overall, the deck can appear in n factorial ways when I fully shuffle them, right? Because of what we explained about what factorial is earlier. And then I'm choosing r cards, right? I'm just taking the top r cards. And the question is, what is the probability that these r cards are the first r numbers? Well, for the first one, right, we can have r different cards that are acceptable, because this can be 1, 2, 3, 4 all the way up to r. Then I'm drawing another card. This time this card will have a r over n. Let's do it like this. This time this card will have a probability of r minus 1, oh sorry, r minus 1, right, over n minus 1. Why? Because sorry, because I have one less card that I want to take. Let's say I've taken one at first, now I have only two to R to pick from, so I have R minus 1 cards which are acceptable, and I have one less card in the deck, so n minus 1 times R minus 2, this just keeps going over n minus 2, and so on until we multiply by 1. We'll have only one card left to draw, and this has to be this specific card, over n minus r minus 1. This is the number of cards I will have left in the deck, right? Because we'll see that this number stays the same, -1 and -1. Here 1 is actually equal to r minus 1, so we'll have at the bottom n minus r minus 1. This stays the same. So this is the probability. The other way we can solve this is by saying this. I'm gonna pick randomly r cards from the deck, right, which will give me n choose r, right? This I'm just picking r random cards. I don't care about the order, but I'm just taking r random cards. This is the amount of r cards that I can take. Now, out of those options, there's only one option in which these are the first consecutive r numbers, right? Now, we know that this is the same as this. This is just the same probability of having the first r numbers, so these are equal to each other, okay? Let's set these equal to each other. We'll do this equal sign and then we're going to solve. First of all, we're going to take the reciprocal of both of these. So on the top, what are we going to have? We're going to have n times n minus 1 times n minus 2 and so on until we'll have n minus r negative 1 like this, and on the bottom we'll have r times r minus 1 times r minus 2, so on until we have until we have 1. We multiply by 1. How can we express this more easily? We want to find the choose function, so I'll put it on the left side like this, just so it will be a bit more organized. The bottom part is just r factorial, right? So n choose r equals, we'll have this, and at the bottom it's r factorial. What do we have at the top? Well, we're multiplying n by its previous numbers up to a certain point. We don't have any sort of notation for that, but what we do have is this notation. We can have n times n minus 1 and so on until 1 over n minus r times n minus r negative 1 and so on until we multiply by 1, right? And then this will cancel out with whatever I have here, and I will be left with this expression right here. Now this we do know, this equals n factorial right at the top, and multiplied by all of its previous numbers over n minus r factorial, because it's n minus r times that negative 1 times that negative 2, all of the previous numbers up to 1. So let's plug that in. At the top we'll have n factorial over n minus r factorial, and of course we can just move this to the bottom and we will get that n choose r equals to n factorial over n minus r factorial times r factorial. Now another thing I wanted to show you this for is we're not going to use a calculator today at all. When you know this equation, it saves like 90% of the time. You won't need a calculator because it just everything cancels out and you're left with very easy numbers. This is one of those cases. So now we can start solving the equation, but let's first of all delete everything here. Where's the eraser? Here, like that. No. Oh, I can use the lasso tool, right? And we throw that away. Okay, let's put this here for the skippers, right? So now we can tackle the question. Flora is going to plant 12 flowers in a row. There are 3 windwheel asters, 4 cecilias, and 5 calla lilies. Calla, I don't know. She plants them in a random order. What is the probability that there are no 2 calla lilies next to each other anywhere? So the first thing I notice, and this is very important because I don't think I've seen any solution that actually uses this. What's the word? Never mind. I didn't actually take it into account. Right? We have no difference between the windwheels and the cecilias. These are the same because I'm only asked about the calla lilies. I can call them whatever I want, but at the end of the day, I have calla lilies and non-calla lilies. Alright, so we're gonna solve it like this. I have 7 non-calla lilies. We're gonna color them white. Do I have a color select here? Yeah, okay, nice. We're gonna color them white, and also I can barely see. Is this the size? Does this have, yeah, okay, this is the size, but why can I not control Z? Okay, we're gonna use this, so I can color this white for a white flower. This is the non lily flower, and I can also have, let's use a red one. Oh, now I can see why I don't, this is, oh, okay, I get it. And we can also have a red flower. Now there are 2 ways to solve it that I saw. One of them was the way I solved it. Another one was actually more like smart. It was easier. This is another way I saw from the comments. And they go as follows. Okay. First of all, we have the 7 white flowers, right? Oh, maybe I'll do like galaxy white. Oh, this is cool. I'll do it in blue so we can actually see. Alright, so I have 7 blue flowers. Alright, let's just color these in randomly. Now what they are saying, 1, 2, 3, 4, 5, 6, 7. What they are saying is, wait, why did you just now decide on where are the spaces are going to be? We have 7 of these, and what we know is that each 2 lilies has to be separated by at least 1 blue flower, one non-lily flower, windwheel or cecilia. At least 1. So let's not give them order. Let's not like assign them spots. And let's first just put 7 of these, 1, 2, 3, 4, 5, 6, 7, and then say in each one of these, okay, in each one of these spots, you cannot see it. In each one of, oh, I can just use this. Can you see it? Yeah, okay, nice. In each one of these spots, I can put a lily. I cannot put 2 lilies in any one of these spots. And then once I have the 12, I can push them in the spots, the gray circles, right? So I can put, I don't know, here and here and here and here and here, for example. This is a valid solution. how do we solve this? What's the math behind it? Well, first of all, these 7 can be in any order, I don't care. Okay? I don't care at all because these are the same. Then I'm gonna have how many ways to put these 5 in 1, 2, 3, 4, 5, 6, 7, 8 spots. By the way, you could have like just 7 plus 1 if you know the fence pole principle. How many ways do I have to distribute 5 flowers in 8 spots? In other words, how many ways do I have to choose 5 spots from these 8? This is just gonna be 5. This is just gonna be here. 5 choose 8. No, other way around. 8 choose 5. Sorry. 8 choose 5. Right? So I have 8 choose 5 different ways to put these here. And then what's the total number of ways overall? What's important about choose and factorial? Usually they go hand in hand, just 2 different ways to solve the same thing. One which accounts for order and the other which doesn't. Here we're not going to account for order. So, because we don't account for order, what we're going to do is say how many total ways do I have to put the 5 lilies? Well, this is just going to be 12 choose 5, right? This time 12 because I can put the lilies in any one of these 12 spots. So the total number of ways is going to be 12 choose 5. So we're going to do 12 choose 5 here. And then we're going to expand. This equals to 8 factorial over 8 over 5 factorial, 8 minus 5 factorial times 5 factorial. All of this over 12 factorial over 12 minus 5 factorial times 5 factorial. Now the way I solve this is just by taking the largest number, because 8 factorial over 8 minus 5 factorial, no, sorry, this here, over 5 factorial, it's just going to cancel out, you know. We're going to be left with 8 times 6 times, 8 times 8 times 8 times 7 times 6, oh my god. These are just going to cancel out to 8 times 7 times 6. This and this is just 7, right? 7 factorial. I'm going to cancel out to 12 times 11 times 10 times 9 times 8. So this equals to 8 times 7 times 6. I'm going to bring this 5 factorial up times 5 factorial. Oh, by the way, no, actually, there's a smarter way to do it. I'm dumb, sorry. We can cancel out the 5 factorials and then do it. So these two are going to be 8 times 7 times 6 times 5 times 4, and these two are going to be 12 times 11 times 10 times 9 times 8. So 7 times 8 times 7 times 6 times 5 times 4 over 12 times 11 times 10 times 9 times 8. Oh, 8. Now you can cancel stuff out. 8 and 8 cancels out. Let's see. 6 can be split into 2 and 3. 2 and 5 cancel with the 10. 3 and 4 cancel with the 12. We're left with, and that's 6. We're left with 7 over 9 times 11. And if you know anything about, if you're familiar with division by a repeating number of 9s, you'll know that this equals to 0.07 repeating, which is a solution. So this is one way to solve it. If you want to solve it by the factorial route, which is what I saw many people do, and I think this is just redundant, is doing it like this. you have, out of this, you can arrange these 7 non-lilies in 7 factorial ways, right? So you have 7 factorial ways to arrange these, and then you have 8 choose 5, right? 8 choose 5 times 5 factorial, because you can also arrange the lilies in 5 factorial ways if you care about the order. And the total number of ways, this is, let's say favorable arrangements, okay, FA, favorable arrangements, and the number of total arrangements, TA, will be just 12 factorial. We can do it this way too, and we'll get the same thing, right? Because let's look at it, okay? Let's zoom to here. We have favorable arrangements over total number of arrangements. So favorable arrangements is gonna be 7 factorial times 5 factorial, I'm changing the order a bit, times 8 choose 5 over 12 factorial. This 7 factorial is just 12 minus 5, right? 7 equals 12 minus 5 factorial. So what we have here, 12 minus 5 factorial times 5 factorial over 12 factorial, this just equals to 1 over 12 choose 5, right? Times 8 choose 5, which is exactly this. This is the same. It's just a more complicated way to look at it. And so our answer is 0.07 repeating. I do wanna show you a different solution, because I think that there's just a lot to learn from here. So let's take all of this and scrap that. Goodbye. Oh, you too, and also you guys. Okay. The other way to solve it, which I think you can learn from, is by saying this. Well, we can split it into 2 options, right? When I have a lily here, I know that it must follow a non-lily, because if it follows a lily, then that's not good. I have a lily here, it must follow a non-lily. I have a lily here, it must follow a non-lily, and so on. Let's say I have a lily here and here, it must follow a non-lily. This is one option, where each lily follows a non-lily. The other option is when, and this is the only other option, is when the last one is a lily, and then it doesn't have to follow anything. So we're going to split it into 2 options, one where every lily follows a non-lily, and one where every lily but the last one follows a non-lily, because the last one is also the last flower. Now if you look at this, we can see that these all are sets, are groups, right? These are groups of, let's call these purple, okay? And also let's take this thing, copy paste into here, 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 and here, right? So these two are just are just a purple one. All of these combinations are just a purple one, and the other ones, they were non-lily earlier, so they remain non-lily. In other words, I have 1, 2, 3, 4, 5, 6, 7 different spots, and I want to arrange 5 groups in them. This is just 7 choose 5, right? This number of favorable arrangements, and like earlier, this is over 12 choose 5, okay? Plus, because this is just one option, right? I have another option where this lily is the last one. In that case, if this lily is the last one, let's see if I can, oh, I can do this. Let's switch these around, and we'll use a red. Now what we're gonna have, well, this red, we already know that this is the last one, so we don't have to even look at it. It's already the last red. What is gonna happen is that this line is gonna go away, this is gonna go away, this is gonna go away, and this is just gonna be a blue one. Okay, this is just gonna be a blue one, because again, this one I don't have to take it into account, I just know it's the last one. This is the option where it's the last one. So here I have still 1, 2, I have 1, 2, 3, 4, 5, 6, 7 different spots, but this time I only have 4 different sets. So this is gonna be 7, choose 4, and again over 12, choose 5 different arrangements. I think a more accurate way to do it is say that first of all I have this number of possibilities plus this number of possibilities, and then this is all over 12, choose 5, but this is the same. Okay, so I have these two, I'm gonna add them, so I have 7 factorial, right, which is gonna be in both of these, so I can just factor it out, over 7 minus 5 factorial times 5 factorial, and of course in parentheses, plus, no, sorry, wait, what I meant to do is this is gonna be here, let's take all of that here, oh, and the dot, thank you very much, and here 1 over plus 1 over 7 minus 4 factorial times 4 factorial. This is gonna be on the top, and on the bottom we'll have 12 factorial over 12 minus 5 factorial times 5 factorial. Now we can solve it. Alright, this is just 2 ways to do it. Let's expand. So we're gonna have 7 factorial times 1 over 7 times, wait, no, 2 factorial, sorry, 2 factorial times 5 factorial plus 1 over 3 factorial times 4 factorial over 12 factorial over 7 factorial times 5 factorial. Now we're gonna do a common denominator, so 7 factorial times, how are we gonna do that? Let's look at the 5 factorial and the 4 factorial. Okay, I only needed to multiply the 4 factorial by 5 in order to get to 5 factorial, and same with the 2 and 3, I need to multiply this by 3 and this by 3 in order to get to 3 factorial, so I have a common denominator. So we're gonna have this I multiply by 3, so 3 plus this I'm gonna multiply by 5 plus 5 over 3 factorial times 5 factorial all over 12 factorial over 7 factorial times 5 factorial. This and this will cancel out. I am left with oh, and we can already arrange this, you know, take this up, take this down. We're gonna have 7 factorial times, this is 8, times 8. These two can just be written as 8 factorial, right? And we said times 7 factorial, we're gonna take this up over the 3 factorial goes down, so 12 factorial times 3 factorial. By the way, if you would have left the 5s in, you would see that this is just like what we did earlier, the 8 choose 5 over 12 choose 5. Now we can start canceling stuff out. First of all, with the 7 and the 3, we're gonna be left with 7 times 6 times 5 times 4. We cancel this out. The 8 times 12, we're gonna cancel this out. It's gonna leave us with 12 times 11 times 10 times 9. And like earlier, the 6 is gonna split into 2 here and 3 here to give us 10 and 12. So these 3 cancel out with the 10 and 12, and we're left with 7 over 11 times 9, which is 7 over 99, which gives us the same solution of 0.07 repeating. I think this is a very cool math problem to show, first of all, different ways of solving, okay, different ways of thinking about the problem. It can show us, it's very good at showing us what is redundant, because doing it in the factorial way, or differentiating between the wind wheels and the Cecilias, you don't have to do that. It's just more calculations, right? So it helps us figure out what we need to do and what we don't need to do, what we need to take into account and what we don't need to take into account. It also is a very great opportunity to learn about choose and factorial and how they work together. You know, how you can solve a question with both ways and have it be the same solution, and see what's easier, right? What do you like more? Here, there's no reason to go in the factorial route. I just use the choose, and of course, eventually the expansion will include a factorial, but we don't need to start solving with factorials, right? When we're thinking about the way of approaching this problem. So this is it. This was very long, but I hope you enjoyed it. I don't know if I'll make other videos like this. I do wanna get into teaching more. Maybe I will find some problems which interest me, and I will make more videos. But yeah, if anyone who's on a lower level saw this and thought it was interesting, helpful, I'll be happy to know I helped. And if any of you liked it and want me to solve something, you can also send it to me. Like if you wanna help or wanna see my way of solving anything, you can also send it my way, and I will be glad to help. And that's it. Have a good day and have a good weekend.